Hey guys, this is a video going through the rest of dataset 4. So in the review video, we were able to identify our independent variables in this scenario as experience. We classified it as nominal with 3 levels, and it was a between subject factor. The same could be said for the type of bow that was used. So experience level broke down into beginner, intermediate, and advanced. Type of bow broke down into bare bow, recurve, and compound. And then in each of these categories, we had 15 different subjects. So we decided that if we were to put this into some organization that would be good for SPSS, we would have one row that had data labels for experience, one row that had data labels for the type of bow that was used, and then one row that represented the heart rate that was measured for each subject. All in all, we decided that a two-way independent ANOVA was the appropriate test to run. And our assumptions for a two-way ANOVA, or two-way independent ANOVA, would be our random sampling, a normal distribution, with no significant outliers for all levels of our independent variable. We've got our variable characteristics, so one dependent variable, that's ratio or interval data. We've got 2 between subject independent variables that are nominal with 2 or more levels. And then we also have our assumption that's tested in SPSS, which is our homogeneity of variance. And we've already covered in our previous examples what the null hypothesis for this would be. So basically that we have equal variances between all levels of our independent variables. When I run this in SPSS, we end up with an output that looks something like this. And the first thing we have to look at in our output is the results of Levene's test or homogeneity of variance to make sure that we know if we've made any violations, but also so that we can kind of be aware if adjustments would have been needed or if there potentially could be something wrong with our data. So Levene's test for our example here shows that we have a p-value of 0.488. So in our answer sheet, we can stick this in. As p is equal to 0.488. Whoops. And this is larger than 0.05, so that tells us that we should accept the null hypothesis and that there are equal variances between all levels of experience and bow types. We then can look at the p-values for the main effects of our ANOVA. So we have a two-way independent ANOVA example, which means that we should have 3 main effects. We should have one for experience, one for bow type, and then the other for the interaction between experience and bow type. Okay. In our output, all of these p-values can be found in our tests of between subjects effects ANOVA table. So we see here experience, our p-value is equal to 0.079, which is larger than 0.05. So we should accept our null hypothesis. And this is the main effect of experience on heart rate. So not having a p-value less than 0.05 means that experience does not have a significant effect on heart rate. Our p-value for our bow type was right underneath our p-value for experience. So p is less than 0.01, which is less than 0.05. That's our alpha level. So in this case, we would reject the null hypothesis and say that bow type has a significant effect on heart rate. The last p-value we are reporting is for our interaction effect, which is 0.010. And that is less than 0.05 as well, so we would reject the null hypothesis and say that there is a significant interaction effect between experience and bow type for our dependent variable measure heart rate. Now, while I am in this test of between subjects effects table, I have the option for you guys to put in the effect sizes for your significant main effects. Experience was not a significant main effect, so we can kind of skip the effect size for that one. However, we did have a significant main effect for bow type. Let me move. I have a section break. I want to move this downward so it's out of the way. So for bow, our effect size is listed in the row associated with bow, and it is our partial eta squared 0.172. Okay, this is larger than our large effect size criteria, so we would say that we've got a large effect size for the differences between bow types. We now can look at our pairwise comparisons. Okay, so I'm just moving through my output here. If I go to pairwise comparisons for bow, okay, I'm going to have those. I'm also going to be looking at pairwise comparisons for the differences between experience levels within each bow type. And then I'll look at the differences between bow types within each experience level. So if I start with these ones, I can see I have significant differences between the bare bow and compound and recurve and compound. So we could say the compound bow resulted in significantly different heart rate when compared to the bare bow and recurve bows. And this would be regardless of experience level. For our first set of pairwise comparisons, this is looking at significant differences between experience levels within each bow type. I've highlighted in here the pairs that resulted in values that were less than 0.05. So we can see within the compound bow group, or people who used a compound bow, there were differences between beginners and advanced, and intermediate and advanced. So we could write this as advanced archers had significantly different heart rate when compared to intermediate and beginner archers who used a compound bow. Okay, we would need to report the effect size for our compound group. So that would be 0.101. And this is looking at differences between experiences, or differences between experienced experience levels, there we go, within bows. I thought I was losing my mind for a second. Okay. Alright, so our effect size is listed as 0.101, and this would be considered a large effect size for the differences between experience levels. For archers who used a compound bow. That works. Okay. The last set of pairwise comparisons is looking at differences between bow types within our experience levels. And we can see from this table that beginners had significantly different bare bow and compound, or heart rates while using bare bow and compound bows. So we could write this as, there was a significant difference in heart rate between bare bow and compound bows in beginners. We also notice differences between compound and recurve and compound and bare bow bow types in the advanced learners. So we could write that one as like heart rate was significantly different for the compound bow when compared to the bare bow and recurve bows. In advanced archers. And we would need to report effect sizes for the beginner group as well as the advanced group. So if we're looking at effect sizes for differences between bows within experience levels, we'll have two effect sizes to report. Or we could kind of combine them also by saying there is a, I'll say this one's like small to medium-ish. It's in between. So we'll say small to medium effect size for the differences between bow types for beginners. And that gave us a partial eta squared of 0.049. And there's a large effect size for advanced archers. Advanced, there we go. And that was a partial eta squared of 0.205. So both of those came from this univariate test down here. All right. So that completes our dataset 4 example. In dataset 5, we were able to identify our independent variable as the type of squat. It was nominal data, 3 levels within subject variable. And we wanted to know what the differences were between squats for our knee range of motion, which we identified as ratio. All in all, we decided that a one-way repeated measures ANOVA would be the best option for this set of data. And the assumption that would be tested in SPSS is our sphericity using Matchley's test. So if we minimize that one and look at data set number 5, this is the output that I was able to generate. The p-value for Matchley's test is 0.037, which is less than 0.05. So we reject the null hypothesis, and we would say that the variances of the differences between all levels of squats, or all types of squats, it also works. They are not equal, so that means we have a violation. We would need to look at our greenhouse geyser box, and we can determine that 0.674 is less than or equal to 0.75. So that tells us we should use the greenhouse geyser adjustment in our ANOVA table. And under squat, in the greenhouse geyser row, we have a p-value of 0.045. So that's the p-value for the main effect of our test. This is less than 0.05. So we reject the null hypothesis, and we would say that type of squat has a significant effect on knee range of motion. Now this was something that I mentioned in the review video. When we have a significant effect, we should look at our pairwise comparisons. And this is one of those rare cases where we didn't end up having significant pairs, likely due to the adjustment that was made using the greenhouse geyser procedures. But if this were to happen on the exam, which I don't think it would, usually I catch those types of things, especially if they're on an exam, or I let you know about it, or I just don't ask. In this case, we would just note that there are no significant pairs, and then just kind of move on with life. So in here, I'm just going to say no significant pairs reported in the pairwise comparisons. Okay. For our effect size, we are using the omega squared formula for a one-way repeated measures ANOVA. And so this formula uses a couple of values. We have K, which represents the number of groupings that we have. We have F, which is the F statistic from the ANOVA table. And then we also have N, which is our sample size. Okay, so those are 3 things that we need to know before we can calculate our omega squared effect size. So I'm going to insert all of this in an equation. That way it's a little bit neater. And our effect size is going to be equal to K minus 1. So K, again, representing the number of groups. We said we have 3 levels. So 3 minus 1. This will be multiplied by F minus 1. So in our ANOVA table, F is 4.364. and we do -1. We repeat this top row, put it in the denominator, and then we add the product of our sample size, which is 12, times our number of groups, which is 3. If you put all of this into Excel, you should get 0.157, which we would argue is a large effect size for the differences between squat types. Okay, so I'll make that red, and I'll make that red. And this would kind of conclude our example for data set number 5. The last set of questions I have given to you guys are for the ANOVA tables. Again, we only will do these calculations for one-way ANOVAs, so I'll give you, well, here, let's do this. I'm going to make this smaller, and we'll go through the scenario. So we have a clinical trial is run to compare weight loss programs. 3 popular weight loss programs are considered: low-calorie diet, low-fat diet, and low-carb diet. For comparison purposes, a 4th group is considered a control group and is included to assess the placebo effect, which is just any normal weight loss due to simply participating in the study. But no intervention was done to that group. A total of 20 patients agree to participate and are randomly assigned to one of the 4 diet groups. So that automatically tells us we're working with a one-way independent ANOVA. Weights are measured at baseline, and patients are counseled on the proper implementation of the assigned diet. After 8 weeks, each patient's weight is again measured, and the difference in weights is computed by subtracting the 8-week from the baseline weight. So that's the value we end up getting in our data table here. Positive differences indicate weight losses, negative differences indicate weight gains. So this would be one of the situations where our dependent variable is an interval type of data. I didn't ask you about that, but just thought I'd point it out. I've given you the sum of squares for the between groups comparison, and then you also have the sum of squares for the within groups comparison. So really what you need to be able to pull out of these types of questions is the sample size, which we noted was 20, and the number of groups, which is 4, right? Low calorie, low fat, low carb, and control. From here, we can start calculating the different components of our table. So the total sum of squares is just the sum of the between and within group sum of squares. So we can just put equals sum and add those two together. Our between groups degrees of freedom is equal to the number of groups that we've collected minus 1. The within groups degrees of freedom is going to be equal to our sample size minus the number of groups we've collected. So that gives us 16. And our total degrees of freedom is the number, or our sample size minus 1, which would give us 19. Mean square is calculated by doing our sum of squares divided by degrees of freedom. We could easily copy this downwards. And then our F statistic is taken by the between mean squared divided by the within mean square, and we get an F statistic of 8.56. Okay. For our repeated measures ANOVA example, we have a researcher is interested in factors that influence a person's ability to remember lists of words. Specifically, they want to know whether the relatedness of the words on the list influence a person's ability to remember them. The 30 participants are given 3 different word lists to learn in random order. Each list has an equal number of words but vary in how words are related. So the categories are unrelated, semantically related, or phonetically related. A 5-minute learning window is allotted for each list, after which each participant must verbally recite as many words as they can remember. The number of correctly stated words is recorded for each subject. So that's what this data represent, or these data represent, right? How many words they were able to remember. Each subject did 3 word lists, so 3 values per subject. Okay. The first thing we can calculate or note in our table is the sample size. So we had 30 participants. Oh, just kidding. I was supposed to change that. This should be 16. Oops. It used to be 30 in the original data set, and then I ended up changing it. T is equal to the number of groups that we have total. So we have 3 conditions, so 3 would go in that box. And then the total number of data points that we have, you could do a count function on this. You can alternatively highlight all of the data and look at the count value at the bottom, 48, or you can multiply 3 by 16. All of them will give you the same value. Our error sum of squares is going to be equal to our total sum of squares minus the condition sum of squares minus the subject sum of squares. Condition degrees of freedom will be equal to the number of groups minus 1. Our subject's degrees of freedom is going to be equal to our sample size minus 1. The amount of error we have is equal to the product of the condition and the subject sum of squares. So you could do this cell times this cell, or if you want to follow the formula I gave you, we could do n minus 1 times t minus 1. Both of them, it'll end up being the same. Okay, because 2 times 15, 30. Woohoo! And then our final total degrees of freedom is going to be equal to our total number of data points minus 1, which gives us 47. From there, our mean squared is calculated by taking sum of squares divided by degrees of freedom in the same row. So we can copy that. And then our F statistic for our condition is the mean squared of the condition divided by error mean square. F statistic for subjects is going to be the mean square for our subjects divided by mean square for error. And we end up getting 4.68. Okay, so if you guys have any questions on how to do any of these, or if you're not sure about some of the processes or interpretations that I wrote, or you want to know if alternative ways of writing things would be acceptable, just shoot me an email and I'm happy to help you out.